In previous classes, you had learned about electric current, battery, electric circuit, and its components. What do you mean by electric current? What is the type of charges flows through the electric wire when it is connected in an electric circuit? Is there any evidence for the motion of charge in daily life situations? You learn about lighting. Lighting is an electric discharge between two clouds or between clouds and the earth. This electric discharge through air appears to us as an electric spark or lighting. Lightning is live example which provides evidence for the motion of charge in the atmosphere. But we are also familiar with continuous steady currents such as in a battery torch. The current goes on as long as the switch is on, producing heat in the bulb and light. Does motion of charge always lead to electric current? Let us see. Activity. Situation 1. Take a bulb, a battery, a switch, and few insulated copper wires. Connect the ends of the copper wires to the terminals of the battery through the bulb and switch. Now switch on the circuit. We observe that the bulb glows. Situation 2. Remove the battery from the circuit and connect the remaining components to make a complete circuit. Again switch on the circuit. We observe that the bulb does not glow because there is no source of electrical energy. Situation 3. Replace the copper wires with nylon wires and connect the nylon wire to the terminals of the battery through a bulb and switch. Now switch on the circuit. We observe that the bulb does not glow because the wires are not conductors. Conclusion. From the above experiment, we conclude that a source of electrical energy and conducting wires are required for the flow of electricity. Electric current. Drude and Lorentz, scientists of 19th century, proposed that conductors like metals contain a large number of free electrons. While the positive ions are fixed in their locations, the arrangement of the positive ions is called lattice. Let us understand the behavior of electrons in lattice space. The electric conductor is nothing but a body which passes the electric current through it. Actually, metals are good conductors of electricity. Conductors having large number of free electrons. These electrons move randomly in all directions in lattice space of a conductor. They can move in any direction. In such a conductor, the number of electrons passing the cross section from right to left in 1 second is equal to that of electrons passing the cross section from right to left in 1 second. Then the net charge moving along a conductor through any cross section is zero. When the conductor is open circuit, what happens to the motion of electrons when the ends of the conductor are connected to battery? After connecting to the battery through the bulb glows because the energy transfer takes place from battery to bulb. These are responsible for transfer of energy. In this situation, there is some net charge crossing through any cross section of the conductor. This order of motion of electrons is called electric current. Now, let us define the electric current quantitatively. Electric current is defined as the amount of charge crossing any cross section of the conductor in 1 second. Let Q be the charge crossing any cross section of the conductor in time t. Therefore, electric current equals to electric charge by time interval. I equals to Q by T. SI unit of electric current is 1 ampere equals to 1 coulomb per 1 second, denoted as 1A equals to 1C by S. Why do electrons move in specified direction when the conductor is not connected to the circuit through a battery? The electrons inside the conductor are in random motion, but when the conductor is connected to a battery, the electrons move in a specified direction. This shows that something causes the electron to move it in a specified direction. When the ends of the conductor are connected to the terminals of a battery, a uniform electric field is set up throughout the conductor. This field makes the electrons move in a specified direction. In which direction do the electrons move? Do the electrons accelerate continuously? Do they move with a constant speed? The free electrons in the conductor are accelerated by the electric field and move in a direction opposite to the direction of the field. When electrons are in motion under the influence of the field, they collide with lattice ions, lose energy, and may even come to a halt at every collision. They are again accelerated by the electric field and make collisions with other lattice ions. In this way, they continue to move along the conductor. The motion of electron is shown in figure. Hence, we assume that electrons in the conductor move with a constant average speed. We call this speed as drift speed or drift velocity. Let us calculate the drift speed of free charges quantitatively. Consider a conductor with cross-sectional area A. Assume that the ends of the conductor are connected to a battery to make the current flow through it. Let Vt be the drift speed of the charges as shown in figure, and N be the unit volume, that is the charge density. The distance covered by each charge in 1 second is Vd. Then the volume of the conductor for this distance is equal to AVd as shown in figure. The number of charges contained in that volume is equal to NAVd. Let Q be the charge of each carrier. Then the total charge crossing the cross-sectional area at position D in 1 second is NQAVd. This is equal to electric current. Electric current I equals to NQAVd. Let us consider it as equation 1. Therefore, drift velocity represented as Vd equals to I by NQA. Let us consider it as equation 2. We know that the charge carriers in a conductor are electrons. The magnitude of electric charge, that is E, is 1.602 into 10 power minus 19 coulombs. Let us calculate the drift speed of electron in a copper wire carrying a current of 1 ampere and cross-sectional area A equals to 10 power minus 6 meter square. The electron density of copper that was found experimentally is N equals to 8.5 into 10 power 28 meter per minus 3. Substituting these values in equation 2 with Q equals to E, we get Vt equals to 1 by 8.5 into 10 power 28 into 10 power minus 6 into 1.6 into 10 power minus 19. Vt equals to 7 into 10 power minus 5 meters per second equals to 0.07 millimeters per second. This shows that the electrons are moving very slowly. Why does a bulb glow immediately when we switch on? When we switch on an electric circuit, irrespective of length of the connecting wire, that is the conductor, an electric field is set up throughout the conductor instantaneously due to the potential difference of the source, that is the battery, connected to the circuit. This electric field makes all the electrons to move in a specified direction simultaneously. How can we decide the direction of electric current? The equation I equals to NQA Vt. In this, the values of N and A are positive. The direction of electric current is determined by the signs of the charge Q and drift speed Vt. For electrons, that is negative charges, Q is negative and Vt is positive. Then the product of Q and Vt is negative. This negative sign shows that the direction of electric current is opposite to the flow or negative charge. For positive charges, the product of Q and Vt is positive. Hence, the direction of electric current can be taken as the direction of flow of positive charges. How can we measure electric current? Usually, an ammeter is used to measure electric current. It is always connected in series to the circuit. Where do the electrons get energy for their motion from? Potential difference. When the ends of a conducting wire are connected to the terminals of a battery, an electric field is set up throughout the conductor. This field exerts a force denoted by Fe on the charge. Let Fe be the force exerted by the electric field on a free charge Q. The free charges accelerate in the direction of the electric field. If the free charges are electrons, then the direction of electric force on them is opposite to the direction of electric field. It means the electric field does some work to move free charges in a specified direction. Can you find the work done by the electric force? Let the electric force make the charges move through a distance L from A to B as shown in figure. We know that the work is the product of force and distance along the direction of force. Hence, work done by the electric force on a free charge Q is given by W equals to Fe into L, work done by the electric force on unit charge equals to W by Q equals to Fe into L by Q. Work done by the electric force on unit positive charge to move it through a distance L from A to B is called potential difference between those points. Potential difference is denoted by a symbol V. The potential difference between two points separated by a distance L in a conducting wire is given by V equals to W by Q equals to Fe into L by Q. This potential difference is also called voltage. The SI unit of potential difference is volt and it is denoted by V. 1 volt equals to 1 joule per 1 coulomb. 1 V equals to 1 J per 1 C. What is the direction of electric current in terms of potential difference? Do positive charges move in a conductor? Can you give an example of this? Let us recall your experience of electrolysis and electroplating and conductivity of fluids that you had learnt in earlier classes. When electric current is allowed to pass through fluids, the positive ions, known as cations, and negative ions, known as anions, move in opposite directions. The direction of the motion of positive charges in an electrolyte is always in the direction of the motion of positive charges in an electrolyte is always in the direction of the electric field, while negative charges move in a direction opposite to that of positive charges. Thus, for conduction in fluids, there exists motion of both positive and negative charges, whereas in case of metal conductors, there will be only motion of electrons. The positive charges are fixed in the lattice. If positive charges move from point A to point B in a conductor, the electric field does positive work, so W by Q is positive for free positive charges. You can say that the direction of the electric field is from A to B, and the point A is at high potential and point B is at low potential. As negative charges always move in a direction opposite to the electric field, we consider that electrons move from low potential to high potential. We know that in a battery or cell, a constant potential difference is maintained till the battery is completely discharged. How does a battery maintain a constant potential difference between its terminals? Why does the battery discharge when its positive and negative terminals are connected through a conductor? To answer this, we need to know about how a battery or a cell works. A battery consists of two metal plates known as electrodes and a chemical known as electrolyte. The electrolyte chemical between the two metal plates consists of positive and negative ion which move in opposite direction as shown in figure. The electrolyte exerts a force called chemical force denoted by Fc. To make the ions move in a specified direction, positive ions move towards one of the plate and accumulate on that. As a result of this, plate becomes positively charged called anode. Negative ions move to another plate and accumulate on that. As a result of this, the plate becomes negatively charged, called cathode. This accumulation continues till both plates are sufficiently charged, but the ions, the motion experiences force called electric force, denoted by Fe. When sufficient number of charges are accumulated on the plates, the direction of electric force, denoted by Fe, is opposite to Fc, and magnitude depends on the amount of charge accumulated on the plates. The accumulation of charges on plates is continuous till Fe becomes equal to Fc. Now, there will not be any motion due to balance of Fe and Fc. The new battery that we buy from the shop is at a stage where the ions in the electrolyte are under the influence of balanced forces. This is the reason for the constant potential difference between the terminals of a battery. What happens when the battery is connected in a circuit? When a conducting wire is connected to the terminals of the battery, a potential difference is created between the ends of the conductor, which sets up an electric field throughout the conductor. The direction of electric field is from positive terminal to negative terminal in the conductor. The large number of electrons in the conductor near the positive terminal of the battery is attracted by it and start to move towards positive terminal. As a result, the amount of positive charge on this plate decreases. So the electric force, denoted by Fe, becomes weaker than chemical force, denoted by Fc, and chemical force pulls negative ions from the positive plate, known as anode, and makes them move towards the negative plate, known as cathode. The negative terminal pushes one electron into the conductor because of stronger repulsion between negative terminal and negative ion. Hence, the total number of electrons in the conductor remains constant, is attained between the forces Fe and Fc. Electromotive force, EMF. When we take an electrolyte is in a beaker, then two rods are placed in an electrolyte. The electrolysis takes place. Positive and negative charges moves towards cathode and positive charges moves towards anode. As a result of this, the plate becomes negatively charged, is called the cathode, and another becomes positively charged, called anode. To move the ions from negative to positive terminal or from positive to negative, so the cathode becomes negatively charged. Negative field is developed in the cathode. To move the negative ions further, we have to do some work because there is a repulsive force acting between negative field and the negative charge. Let us assume that work done by the chemical force to move a negative charge from positive to negative terminal against the electric force Fe be W, and also assume that the magnitude of chemical force is equal to magnitude of chemoelectric force, denoted by Fe. The work done on negative charge, denoted by Q, by the chemical force W equals to Fed. Then work done by the chemical force to move 1 coulomb charge from positive terminal to negative terminal is given by W by Q equals to Fcd by Q. We know that Fc equals to Fe. Then we get W by Q equals to FAD by Q. Then W by Q is the work done by the chemical force on unit positive charge to move it from positive to negative terminal. This is called EMF, denoted by E, where E equals to W by Q equals to FAD by Q. Generally, EMF is defined as the work done by the chemical force to move unit positive charge from negative to positive terminal of the battery. How can you measure the potential difference or EMF? Generally, a voltmeter is used to measure PD or EMF across an electric device like battery. It must be connected in parallel to the electric device to measure the potential difference across the ends of the electric device. When a battery in a torch is used for several weeks, the light from its bulb becomes dim. We say that the battery or cell in the torch is discharged. What does it mean? Is there any relation between EMF of a battery and drift speed of electrons in the conductor connected to a battery? Ohm's law, lab activity. Aim: to show that the ratio V by I is a constant for a conductor. Material required: 5 dry cells of 1.5 volt each, conducting wires, an ammeter, a voltmeter, and thin iron spoke of length 10 cm, LED, and key. Procedure: connect a circuit as shown in figure. Solder the connecting wires to the ends of the iron spoke. Close the circuit. Note the readings of current from ammeter and potential difference. Now connect 2 cells in series. Instead of one cell in the circuit, note the respective reading of the ammeter and voltmeter. Repeat the same for 3 cells, 4 cells, and 5 cells respectively. Record the values of potential difference denoted by V and current denoted by I corresponding to each. Find the ratio of V by I every time. We find that the ratio V by I is a constant. We can write this mathematically as V is directly proportional to I. V by I is equals to constant. This constant is called resistance of the conductor. It is denoted by R. Then we get V by I equals to R. V equals to IR. Draw a graph between V and I, taking the current denoted by I on y-axis and potential difference denoted by V along x-axis with appropriate scale. You will get a straight line graph passing through the origin. Repeat the process by using a LED instead of iron spoke. Connect long terminal of LED to the positive terminal of the battery. Connect the short terminal of the LED to the negative terminal of the battery. Note the values of current denoted by I and potential difference denoted by V in each case, and record the values. You will notice that the ratio V by I is not a constant. Draw graph between V and I from LED. We will get a curved graph. From the above lab activity, we can conclude that the ratio between V and I is not constant for some materials at constant temperature. This space was popularly known as Ohm's law. The SI unit of resistance is ohm. The symbol of ohm is ohm. 1 ohm equals to 1 volt per 1 ampere. 1 ohm equals to 1 V by A. Limitations of Ohm's law. Ohm's law is not a fundamental law of nature, but commonly found property many substances under certain conditions. In many cases, the relation between V and I is different. V depends on I non-linearity. The relation between V and I depends on the sign on V for the same absolute value of V. The relation between V and I is not unique. That is, for the same current, I is more than one value of voltage V. Ohm's law is not applicable to gaseous conductors. It is also not applicable to germanium conductors and silicon. And for changing the temperature, resistance of a material also changes. Hence, VI graph for a conductor will be nonlinear. While a conductor is connected to a circuit, now electrons start moving in a specific direction. During this motion, there may be a chance to collide the electrons with positive ions. During this collision, some mechanical energy is loses and converted in the form of heat. But there is a field of electricity in the conductor. With the help of that electron, regains the energy in the field, and motion of electrons takes place. This opposition offered to the flow of electrons in a conductor by lattice ions depends upon nature of the material. Therefore, resistance is defined as the obstruction to the motion of electrons in a conductor. The material which offers resistance to the motion of electrons is called the resistor. Is there any application of Ohm's law in daily life? What causes electric shocks in a human body, current or voltage? Let us see. Electric shock. Let us assume that human body is a resistor. The resistance of the human body generally varies from 100 ohms. If body is wet with salt water, to 5 lakh ohms. If the skin is very dry, let us calculate the amount of current that flows through the human body. Let us assume you have touched the 2 electrodes of a battery of 24 volts with dry fingers in such a way that the circuit is complete. Let your body resistance be 1 lakh ohms. Then the current flowing through your body is given by I equals to 24 by 1 lakh equals to 0.00024 amperes. This current is very small. When such small current passes through the human body, it does not affect the functioning of various organs inside the body. Do you know the voltage of mains that we use in our household circuits? What happens to our body if we touch live wire of 240 volts? 240 volt current disturbs the functioning of organs inside the body. It is called electric shock. If the current flow continues further, it damages the tissues of the body, which leads to decrease in resistance of the body. When this current flows for a longer time, damage to the tissues increases, and thereby the resistance of human body decreases further. Hence, the current through the human body will increases. If this current reaches 0.07 amperes, it affects the functioning of the heart and If this much current passes through the heart for more than 1 second, it could be fatal. If current flows for a longer time, the person in electric shock is being killed. See the table that describes the effects of electric current on human body. Current in ampere effect 0.001 can be felt. 0.005 is painful. 0.010 causes involuntary muscle contractions called spasms. 0.015 causes loss of muscle control. 0.070, if through the heart, causes serious disruption, probably fatal if current lasts for more than 1 second. From the above discussions, we can conclude that an electric shock can be experienced when there is a potential difference exists between one part of the body and another part. When current flows through human body, it chooses the path which offers low resistance. The resistance of a body is not uniform throughout it. For example, skin offers more resistance than the organs inside the body. As long as current flow continues inside the body, the current and resistance of human body goes on changing inversely. Hence, the electric shock is a combined effect of potential difference, electric current, and resistance of human body. Why does not a bird get a shock when it stands on a high voltage wire? There are two parallel lines carrying 240 volts current. The voltage current will pass through the body if both the wires are touched at the same time. But when the bird sits on only one wire, there is no potential difference between the legs, so current passes through the bird. Hence, it does not feel any electric shock. Do you know? A multimeter is an electronic measuring instrument that combines several measurement functions in one unit. Digital multimeter displays the measured value in numerals. A multimeter has three parts. Display. The display usually has 4 digits and the ability to display a negative sign. Selection knob. The selection knob allows the user to set the multimeter to read different functions such as milliamps denoted by mA of current, voltage denoted by V, and resistance denoted by ohm. Ports. Multimeters generally have 2 ports. One is usually labeled as COM, common or ground port. This is where black touch LED is connected. The other is labeled as MAV, ohms, port, where the red LED is conventionally plugged in. Warning: most multimeters can measure AC quantities only, but AC circuits can be dangerous, so measure DC quantities only. Temperature and resistance. Whenever an electrons are moving through the conduction, if we increase the temperature of the conductor, then the energy of the system increases, then the motion of electrons or the velocity of electrons or drift velocity of electrons increases. During this process, collisions takes place. Some of energy of the electron is loses and some heat energy is developed. Because of this reason, the number of electrons flowing through the particular region decreases, so opposing force increases, that is, resistance. So resistance is proportional to temperature. Nature of material and resistance. collect different metal rods of the same length and same cross-sectional area like copper, aluminium, iron, etc. P and Q are the free ends of the conducting wires. Connect one of the metal rods between the ends P and Q. Switch on the circuit. Measure the current using the ammeter connected to the circuit and note it in your notebook. Repeat this with other metal rods and measure electric current in each case. We notice that the values of current are different metal rods for constant potential difference. Hence, we conclude that the resistance of a conductor depends on the material of the conductor. What happens to the resistance of a conductor if we increase its length? Length of the conductors and resistance. Collect iron spokes of different lengths with the same cross-sectional areas. Make a circuit as shown in figure. Connect one of the iron spokes, say 10 cm length, between P and Q. Measure the value of the current using the ammeter connected to the circuit and note the value in your notebook. Repeat this for other lengths of the iron spokes. Note corresponding values of currents in your notebook. We observe that current decreases as the length of the spoke increases. We know that resistance increases as current decreases. Hence, the resistance of iron spoke increases as its length increases. We conclude that the resistance of a conductor is directly proportional to its length for a constant potential difference and constant cross-sectional area. That is, R is directly proportional to I at constant temperature and cross-sectional area. Let us consider it as equation 1. Cross-section area and resistance. Collect iron rods of equal length but different cross-section areas. Make a circuit as shown in figure. Connect one of the rods between points P and Q. Note the value of the current using the ammeter connected to the circuit and note it in your notebook. Repeat this with other rods. Note the corresponding values of currents in each case and note them in your notebook. You will notice that the current flowing through the rod increase with increase in its cross-sectional area. Hence, the resistance of a rod decreases with increase in the cross-section area of the rod. From this activity, we conclude that the resistance of a conductor is inversely proportional to its cross-section area. That is, R is directly proportional to I by A at constant temperature and length of the conductor. Let us consider it as equation 2. From the equations 1 and 2, we get R is directly proportional to I by A at constant temperature. R equals to rho I by A. Here, rho is proportionality constant and it is called specific resistance or resistivity. See figure to get clear picture of this equation. Specific resistance depends on the temperature and nature of the material, whereas the resistance of the conductor depends on nature of material. Temperature and geometrical factors like length and cross-section area of the conductor. The SI unit of resistivity is ohm per meter. The reciprocal of resistivity is called conductivity. The values of resistivity of material determine their conductivity. Metals with low resistivity behave as good conductors. Metals such as copper are therefore used for making electric wires. The filament of an electric bulb is usually made of tungsten because of its higher resistivity values and melting point, that is 4322 degrees Celsius. The values of resistivity of insulators are very high, of the order of 10 power 4 to 10 power 16 ohms per meter. Alloys like nichrome, which includes nickel, chromium and iron, and manganese, which includes 86% copper, 12% manganese, 2% nickel, have 30 to 100 times larger values of resistivity than those of metals. This makes them suitable for use in the heating elements of electric irons, toasters, etc. These alloys also have the advantage that their resistance varies very little with temperature and they do not oxidize easily. The resistivity of materials such as silicon and germanium are 10 power 5 to 10 power 10 times more than that of metals, but 10 power 15 to 10 power 16 times less than that of insulators. Such materials are called semiconductors. Semiconductors are used to make diodes, transistors, and integrated circuits, also known as ICs. ICs are used in all sorts of electronic devices, including computer, TV, mobile phones, etc. Electric circuits, a closed path created by the connecting wires through a battery along which electrons can flow, is called a circuit. For the continuous flow of electrons in the circuit, it must be a complete circuit with no gap is left in between. Usually, a gap is provided in the circuit for connecting of a switch is used to make or break of an electric circuit. Circuits may have more than one device that receives electric energy from the source. These devices are commonly connected in the circuit either in series or in parallel. When the components of the circuit are connected in series, in this situation, there will be a single path for flow of electrons between the terminals of a battery, generator, or wall socket. When these devices are connected in parallel, in this case, they provide a separate path for the flow of electrons. But both series and parallel connections have their own distinctive characteristics. Series connection of resistors. Take different bulbs, measure their resistances with a multimeter. Note their values in your book as R1, R2 and R3. Connect them as shown in figure. Measure the potential difference between terminals of the battery connected to the circuit. Measure the potential differences between the ends of each bulb and note them as V1, V2 and V3 from voltmeters in your notebook. Compare the potential difference of the battery and resistors. What do you notice? The sum of the potential difference of the bulbs is equal to potential difference across the combination of the resistors. Then we get V equals to V1 plus V2 plus V3. Let us consider it as equation 1. Measure the value of the current flowing in the circuit with the help of the ammeter. Note its values in your books as I. What do you notice? Equivalent resistance of a series connection. In this figure, the bulbs are shown as resistors with symbols. In series connection of resistors, there is only one path for the flow of current in the circuit. Hence, the current in the circuit is equal to I. By Ohm's law, potential difference denoted by PD across R1 is V1 equals to I R1. PD across R2, V2 equals to I R2. PD across R3 is V3 equals to I R3. Let Req is the equivalent resistance of the combination of resistors in series. What do you mean by equivalent resistance? If the current drawn by a resistor is equal to the current drawn by the combination of resistors, then the resistance is called as equivalent resistor, provided the source in the circuit is constant. So, we have V equals to I Req. Substituting the values of V1, V2, V3 and V in the equation 1, we get I Req equals to I R1 plus I R2 plus I R3. Req equals to R1 plus R2 plus R3. From the above equation, you can conclude that the sum of individual resistance is equal to their equivalent resistance when the resistors are connected in series. What happens when one of the resistors in series breaks down? When one of the resistors in series breaks down, the circuit becomes open and flow of current cannot take place in the circuit. This is the reason why household electrical appliances are not connected in series. Can you guess in what way household wiring has been done? Let us see. Parallel connection of resistors. Connect the bulbs as shown in figure. Measure the potential difference across each bulb using a voltmeter or multimeter. The potential difference at the ends of each bulb is the same. These bulbs are said to be in parallel connection. Measure electric currents flowing through each bulb using ammeters. Let I1, I2 and I3 be the currents flowing through R1, R2 and R3 resistors respectively. Measures the current denoted by I drawn from the battery using the ammeter 1. We will notice that the current drawn from the battery is equal to the sum of individual currents drawn to the bulbs. Then I equals to I1 plus I2 plus I3. Let us consider it as equation 1. Equivalent resistance of a parallel connection. According to the Ohm's law, current through R1 is I1 equals to V by R1. Current through R2 is I2 equals to V by R2. Current through R3 is I3 equals to V by R3. Let Req be the equivalent resistance of the resistors is parallel. It is shown in figure. Then we get I equals to V by Req. Substituting the values I, I1 and I3 in equation 1, we get V by Req equals to V by R1 plus V by R2 plus V by R3. 1 by Req equals to 1 by R1 plus 1 by R2 plus 1 by R3. Let two resistors R1 and R2 are connected in parallel. 1 by Req equals to 1 by R1 plus 1 by R2. Req equals to R1 R2 by R1 plus R2. The equivalent resistance of a parallel combination is less than the resistance of each of the resistors. You can use this result to explain why the resistance of a metal wire is inversely proportional to its area of cross section. Let us imagine a thick wire as a parallel combination of several thin wires. Then the resistance of the combination is less than that of each thin wire. In other words, the resistance of a thick wire is less than that of a thin wire. Through the methods discussed in the previous section for replacing series and parallel combination of several thin wires, in other words, the resistance of a thick wire is less than that of a thin wire. Combination of resistors. In order to get a particular desired value of resistance in a circuit, sometimes we have to connect two or more resistors. They can be connected in series or parallel or both in series and parallel. When the resistance of a circuit is to be increased, they are connected in series, and when the resistance of a circuit is to be increased, when the resistance of a circuit is to be decreased, in order to pass a heavy current in the circuit, they are combined in parallel. Through the methods discussed in the previous section for replacing series and parallel combination of resistors, they are not sufficient for the analysis of many simple circuits, particularly those containing more than one battery. Let us see Kirchhoff's law. Two simple rules called Kirchhoff's rules are applicable to any DC circuit containing batteries and resistors connected in any way. Junction law. At any junction point in a circuit where the current can divide, the sum of the currents into the junction must equal the sum of the currents leaving the junction. This means that there is no accumulation of electric charges at any junction in a circuit. From figure, we have I1 plus I4 plus I6 equals to I5 plus I2 plus I3. This law is based on the conservation of charge. Loop law. The algebraic sum of the increases and decreases in potential difference across various components of the circuit in a closed circuit loop must be zero. Otherwise, one can continuously gain energy by circulating charge around a closed loop in a particular direction. This law is based on the conservation of energy. Example, let us imagine a circuit loop. The potential difference between the 2 points at the beginning of the loop has a certain value. As we move around the circuit loop and measure the potential difference across each component in the loop, the potential difference may decreases or increases depending upon the nature of the element, like a resistor or a battery. But when we have completely traversed the circuit loop and arrived back to our starting point, the net charge in the potential difference must be zero. Let us apply loop law to the circuit shown in the figure. For the loop ACD BA minus V2 plus I2 R2 minus I1 R1 plus V1 equals to 0. For the loop EFD CE minus of I1 plus I2 into R3 minus I2 R2 plus V2 equals to 0. For the loop EFBAE minus of I1 plus I2 into R3 minus I1 R1 plus V1 equals to 0. Example, find electric current drawn from figure from the battery of EMF 12V. Solution, let I equals to I1 plus I2 be the current drawn from EMF of 12V. From the figure, using the loop law, for the loop DABCD minus 3 into I1 plus I2 plus 12 minus 2I1 minus 5 equals to 0. Let us denote it as A. For the loop DAFED minus 3 into I1 plus I2 plus 12 minus 4I2 equals to 0. Let us denote it as B. Solving the equation A and B, we get I1 equals to 0.5A and I2 equals to 1.5A. Total current drawn is then I equals to 0.5 plus 1.5 equals to 2A. Electric power. In our daily life, we may use many devices to do what? In all these cases, we use electrical energy with the help of that within less period of time doing more work. When an electric current is passed through an electric wire, the filament gets heated up and electric energy is converted into heat energy. Consider that a charge denoted by Q, coulomb, passes through a point A, moves to point B in the time interval t seconds. Let V be the potential difference between the points A and B. The work done by electric field in time t is given by W equals to QV. Let us consider it as equation 1. The work is equal to the energy lost by the charge while passing through the conductor for time t. Therefore, energy lost by the conductor in 1 second equals to W by T. From equation 1, W by T equals to QV by T. Let us consider it as equation 2. We know Q by T equals to 1 and W by T equals to P, which is the power. Then from equation 2, which implies P equals to VI. Let us consider it as equation 3. This equation can be used to calculate power consumption by any electric device that is connected in a circuit. From Ohm's law, V equals to IR. Therefore, from equation 3, which implies P equals to I2R or V2 by R, let us consider it as equation 4. To know the power that can be extracted from a battery or any source can be calculated by P equals to EI, whose E is the EMF of the battery. Example. Let us consider an example to understand power consumption. A bulb is marked 60 watt and 120 watt. This means that if this bulb is connected to 120 volt source, it will able to convert 60 joule of electrical energy into heat or light in 1 second. From the marking of bulb, we can measure the resistance of the bulb. From the relation P equals to V2 by R, which implies R equals to V2 by P. Substituting the values V and P in above equation, we get R equals to 120 into 120 by 60 equals to 240 ohms. Thus, the bulbs marked as 60 watts and 120 volts will offer a resistance of 240 ohm with a flow current through it in normal condition. If this bulb is connected to the 12 volts a battery, the consumption by the bulb is given by P equals to V2 by R equals to 12 into 12 by 240 equals to 3 by 5 equals to 0.6 watt. Since watt is a small unit of power, a bigger unit, kilowatt, is generally used to express power consumption. 1 kilowatt equals to 1000 watts equals to 1000 joule per second. What do you mean by 1 unit? In household consumption of electrical energy, 1 unit in household consumption of electrical energy is equal to 1 kilowatt hour. 1 kilowatt hour equals to 1000 watts into 1 hour. 1000 watt into 60 seconds. 1000 joules per second into 3600 seconds equals to 36 into 10 power 5 joules. What do you mean by overload? Electricity enters our homes through 2 wires called lines. These lines have low resistance and the potential difference between the wires is usually about 240 volts. All electrical devices are connected in parallel in our home. Hence, the potential drop across each electric device is 240 volts. Based on the resistance of each electric device, it draws some current from the supply. Total current drawn from the mains is equal to the sum of the currents passing through each device, known as junction law. If we add more devices to the household circuit, the current drawn from the mains also increases. This leads to overheating and may cause a fire. This is called overloading. If we know the value of resistance of the electric device, we can calculate the current passing through it using the equation I equals to V by R. For example, the current passing through a bulb with R. Why do we use fuses in household circuits? To prevent damages due to overloading, we connect an electric fuse to the household circuit. In this arrangement, the entire current from the mains must pass through the fuse. The fuse consists of a thin wire of low melting point. When the current in the fuse overloaded, the wire will heat up and melt. Now the circuit becomes open and prevents the flow of current. So all electrical devices are saved from damage that could be caused by overload. How can we prevent damage due to overloading? To prevent damages due to overloading, we connect an electric fuse to the household circuit as shown in figure. In this arrangement, the entire current from the mains must pass through the fuse. The fuse consists of a thin wire of low melting point. When the current in the fuse exceeds 20 amperes, the wire will heat up and melt. The circuit becomes open and prevents the flow of current into the household circuit. So all the electric devices are saved from damage that could be caused by overload. Thus, we can save householding wiring and devices by using fuses. Note: the value of overload current varies from the household currents.